Go ahead.
Okay, so welcome everyone. Today we have Professor Kirk Madison, who's going to tell us about atomic sensors for vacuum metrology, status of the field. Okay.
Thank you so much for the introduction. I'm going to try to gesture as much as possible using my mouth so that people online can see, as well as people in the room. So thank you for this invitation. I gave a talk on this topic about 2 years ago at the QMI, and so in 2023, and a lot has happened since then. And so I'd like to give you an overview of the status of the field and what's happened since I last spoke at UBC. Please interrupt me if you can't hear, or anyway, if there are any technical issues. So so this work is a big collaboration. So actually, I don't see my mouse. My apologies. Give me just a minute. I'm going to create a PDF so that I can gesture with my mouse. Okay. Yes. Oh, oh, indeed. Okay. Yes. Thanks for the heads up. Okay. Right. So as I was saying, this is a big collaboration. My collaborators include James Booth from DCIT and Roman Krims from here at UBC. And we also have colleagues at NIST in the US who've contributed, and of course they have their own effort that I'll be talking about as well. The work I'll be showing you is quite a bit of work from people in my group, including Henry Shin, who's now at Quantum Valley Labs and Waterloo, Riley Stewart, Avinash, Eric Freeland, who's now a postdoc at Triumph, Dennis Uland, and Perrin also was involved in creating a portable cold atom sensor that now is in Berlin. Well, actually, it's back at UBC being fixed. And not pictured are Xu Yang Gao, who's a PhD student of Romans, and Felix Klose and Boyan Yu, who are students in my group now working on the next steps. So I'm going to begin with a bit of kind of motivation for the field. So as most of you probably know, our time and frequency standards are defined by atom. Here's a picture of Charles Towns building a maser back in the 50s. And atoms have a variety of advantages. They're single quanta of matter, and they provide, at least as far as clocks are concerned, the best clock you can make. And as a sensor, they have generically the following advantages. These sensors are immutable natural objects. They never age. There's no fabrication errors. You buy a bottle of rubidium from your favorite element store, it's always the same. There are no calibrations in principle are not necessary. So, so this makes them like ideal for sensing a variety of phenomena. This includes building magnetometers to sense magnetic fields, Rydberg sensors for measuring electromagnetic or electric fields. People make accelerometers to measure gravitational fields. And people also use atoms as quantum transducers. Of course, our time and frequency standards are based on atomic clocks. And so we set out to develop a new quantum sensor for pressure standards. So I'll explain what I mean by that. As a brief note on standards and realizations, so a standard is a fundamental definition of a unit, say, for example, the second. And a realization of a standard is a practical method used to realize this standard in some application, a measurement application. So an example is the meter is defined as the distance light travels in vacuum during 1/299,000 or millionth of a second. And the realization, of course, is you take a helium neon laser and you lock it to an iodine transition, and some number of wavelengths of this radiation defines the meter, or let's say realizes the meter. The second is an interesting outlier. In a sense, the standard is the same as the realization. You take an atom, a cesium atom in this case, and the energy splitting between the FeCl3 and FeCl4 ground states is this number, 9.1926 so-and-so gigahertz. And so the second is defined in terms of this energy splitting. Literally, it is the duration that this number of periods would take. So if you, or said another way, if I made an oscillator that drove this transition, that oscillator would be oscillating at this frequency, and this number of periods would define a second. So in metrology, vacuum metrology, there are a number of ways we can motivate why this is important. Measuring vacuum is important for, say, for example, aerospace and very low Earth orbit. The vacuum that satellites experience is between about 10 to the minus 4 Pascal and about 10 to the minus 7. If you do device fabrication, say, for example, Kudzu here at UBC does molecular beam epitaxy, and their growths occur at pressures ranging from about 10 to the minus 6 Pascal down to as low as even 10 to the minus 10 Pascal. And this delineates the high vacuum, ultra high vacuum, and extreme high vacuum regimes. And at present, there are a number of methods for measuring pressures or densities at these very low pressures. And they're here, shown here in red, ionization gauge and residual gas analyzer. They're both based on ionization. You ionize the particles in the vacuum and you collect the ions and you count them. And that tells you how many neutral particles there are in your vacuum. And these methods, they're not primary. So these are gauges that have to be calibrated, and they're typically calibrated using a mercury manometer. So, technology from the 16th century, which it gets extended by a so-called orifice flow standard. I'll explain what that is in a moment. So one of the problems with the orifice flow standard is it's not primary, it's linked to a manometer, and it's limited to measuring inert gases only. So let me explain what this classical standard is. So you take a mercury manometer and you stabilize a pressure in some region, and then you push a piston into this vessel, which I'm going to call a flow meter, and out comes a certain volume of gas. And that volume of gas, since you know the pressure, because you're stabilizing it to a mercury manometer, is some mass flow Q. So this gas comes out of this pipe, and it flows through an orifice, a very precisely machined orifice, of a known conductance C. And the pressure in this upper chamber P1 is related to the conductance and this mass flow Q by this formula, Q over C, with some correction factor, which relates to the pressure differential, or the pressure ratio of these two, which can be measured at high pressure. And then you can run this orifice flow at low pressures, where you might have trouble measuring this pressure, but you can create a pressure, a known pressure P1 using this, this technique. So this is what every metrology, every vacuum metrology group around the world uses to calibrate ion gauges. They have a giant room with temperature-controlled mercury manometers, flow meters, and they flow gas into a chamber, and then they put a gauge on that they want to calibrate. They create a known pressure, and they just read off the ion current, and they say that ion current corresponds to this pressure of this gas. So the problem with this is that it only works for inert gases because you need the gas to flow in and flow out. If the gas flows in and then sticks to the walls or reacts with something, all bets are off. So this only works for things like argon and nitrogen, non-sticky species. As I mentioned before, the ionization gauge. So this is how a pressure standard works. The ionization, the principle for ionization detection, an ionization-based particle detector is as follows. I have some filament, basically like an incandescent bulb. I pass current through it, electrons boil off. So this thing glows bright, like a light bulb. Electrons come flying off of this thing. They're attracted to a grid, a cylindrical mesh, which is positively biased. The electrons fly through this grid, and then there's a ion collector, which is ever so slightly negatively charged. So the electrons avoid this center pin and fly through and come back again. They orbit around, and this is a top view showing like the electrons coming out and how they orbit in this region. If a neutral particle enters into this region, it may get impact ionized by an electron. And when it does, it's now a positively charged ion, and it will drift towards this ion collector. And that current, the rate at which these ions are hitting this collector, is proportional to the number of neutral particles entering this region per unit time. So the problem with this device is that it depends on the electron hitting these atoms and ionizing them, and that probability isn't unity. And so you have to measure a current, you have to create a known pressure, measure a current, and then you can calibrate the gauge. And any kind of coating, if you flow some other gas and you coat the surfaces, that changes the work function on the surface, and that changes the electric field, which changes the electron plasma density, which changes the calibration. So ion gauges are notoriously, they're used everywhere, they're ubiquitous, but they're notoriously imprecise. Okay, so this motivates, hopefully, why vacuum metrology is important, why it might be important, and why the atom is maybe a good candidate for a sensor. So the idea here is, how are we going to use a sensor atom as how are we going to use an atom as a sensor of some other particle? Well, it's quite simple. We just wait for a collision to occur, and then we measure or detect these state changes of the sensor atom induced by the collision. So we prepare a quantum state, and we check if the quantum state has been perturbed. If it has, it's perturbed because it got hit. If it hasn't, it hasn't gotten hit yet. And we just measure the rate at which these state changes occur. And that's related to the density of the gas in the vacuum. So there's a bunch of different states we could consider. You could consider the internal state of the atom. You could say, for example, look at the state populations of the internal states. You could also create some quantum superposition of internal states and look for some kind of decoherence. This is what plagues people who make atomic clocks. These collisions produce a shift. Not only do they decohere the qubit or the clock, they also shift its frequency. You could also look at the external state. So basically the momentum, like, when this particle hits this atom, it's going to kick it with some momentum. So we could prepare an atom, initially it's stationary atom, and just check if it gets hit, it'll start moving. So all of this, of course, requires preparing the atom's initial state. And by that, I mean its initial quantum state, because you need to, well, the cross-section for these processes will depend on the internal state. And you also need to prepare the atom at basically stationary. We need to make the atom stationary in order for this to work, or at least you need to know the momentum of the atom as your initial state and to see a change. So anyway, I'm going to talk about looking at the recoil, the momentum recoil of the atom as a detector. And I'll mention that this quantum decoherence that I've talked about is relevant for atom and ion-based quantum computers. So in fact, one of the major decoherence mechanisms for ion-based quantum computers is background collisions in a vacuum. So understanding these and what role they play in decoherence of quantum information is top of mind for many people in this field. Okay, so the idea is very simple. Imagine I have a flux of particles. Their density is n. Their average velocity is v. The sensor atom presents some target with a cross section, and the rate of collisions is simply n times sigma times v. And so if I want to know n, I just measure gamma and I divide by sigma v and I get n. Simple enough. That's the basic idea. So this raises two questions. How do we know sigma v? We need to know that. Gamma we measure. And how do we know that we know sigma v? You know it, but how do you know that you know it? This is a key point for metrology. Okay, so here's a picture of some atoms. The length scale here is about 3 centimeters. So this cloud is like 5 millimeters in size. This is a cloud of about 1 billion lithium atoms at 500 microkelvin. They're glowing because we're shining light on them. This light is resonant, so they scatter these photons and we collect them on a camera. It's very visually appealing, but we don't want this light on when we do this measurement, so we put the atoms in so we hold them in a trap. We don't hold them in this trap. We hold them in a magnetic bottle, and we hold them in the trap because we want to hold them for a long time and wait for collisions to occur. So as I said before, the collision rate will be something like n sigma v. And so you would expect the atom number in the trap to decay exponentially, and that's what we see. This is some data. This is the atom number as a function of time. Decays exponentially, and you can just read off gamma. So so if I have multiple atoms in my background, I'll have some collision rate, which is the sum of collision rates from each species. So n sigma v for each species I. So this gamma is the aggregate loss rate for all those collisions. Now, one caveat is that even though the particles are room temperature and my atoms are like, less than a millikelvin, so it's like 300,000 times difference in energy scales, not every collision will actually knock an atom out. This seems surprising. It should be surprising to you. But not every collision generates loss. So to illustrate this, I'm showing you here data of the loss rate as a function of, say, argon pressure. I crank up the argon pressure, and I see the loss rate increasing linearly. The slope of this line is just sigma v for argon, hitting rubidium. We had rubidium atoms in this case. So here's my loss rate curve. Actually, here's my atom numbers of function of time. I just fit for gamma, and then I change the argon density. This gets faster, and I just plot another point there. And so here's my gamma versus argon. This is for a shallow trap. If I make a trap deep, if I make the trap deeper, then less of the collisions generate loss. At the same pressures, I have a loss rate which is dramatically suppressed. So I can plot the sigma v for each of these curves as a function of the depth of my trap. Yeah, so here I'm saying not every collision leads to loss, so the slope is less. So I can plot this sigma v as this is the loss cross section as a function of trap depth, and this is what we see. So when the trap depth is shallow, very shallow, check this out. So this is in millikelvin. So this is 1 millikelvin. This is 100 microkelvin. So when my trap depth is 100 microkelvin, then every collision generates loss, meaning sigma loss v, this curve here, equals the total collision rate, sigma v, times the density, right? When I crank up the trap depth, I start to see a reduction, like the loss rate is lower than the total collision rate. Not every collision generates loss as I crank up the trap depth. When I get to about a Kelvin, here's a Kelvin, you can see the loss rate is 1 1/5 of the total collision rate. So only 1 out of 5 collisions actually ejects an atom from a trap at 1 Kelvin, even though the incoming particles are at 300 Kelvin. These are room temperature atoms hitting my cold atoms. Even more surprising, check this out, like the median collision energy, the point at which this is about half, is around 20 millikelvin. So I have a background gas of 300 Kelvin hitting a stationary atom. Half of the collisions are imparting less than 20 millikelvin of energy to my trapped particle. That's should be astounding to you. Why in the world should that be the case? What sets the 20 millikelvin? Where'd that number come from? What's it got to do with 300 Kelvin? Nothing. Has nothing to do with it. This is purely a quantum mechanical effect. So I can write the loss rate as the total collision rate, N times sigma V total, times something that looks like 1 minus P, where P is the probability the particle will be retained. So P is like the difference between, the loss rate and the total collision rate. And what is this probability of the particle retained? How is it related? It's simply the cumulative distribution function of the transferred energy distribution up to my trapped depth. So this red curve here is supposed to be a cartoon picture of what the energy distribution looks like, the transferred energy distribution. And if I just integrate that up to the trapped depth, the area under this curve is the probability that the particle will have less than that energy, U. So that's what I'm plotting here. This is the CDF. And so the shape of this curve tells us something about the shape of the transferred energy distribution, the averaged over all the collisions, right? This is a thermal average. And anyway, so we're going to come back to this later. Yeah, so, okay, in summary, because the loss rate varies so much with trap depth, in order to actually extract N, you need to know sigma total, but you also need to know the trap depth because you need to know what this P is, what this retained fraction is. So in general, you need to know the trap depth and you need to know sigma loss V. And also you have to know the energy distribution of the atoms in the trap because if an atom's already moving, it takes less energy to get out. So there's some complications, but you get the point. Okay, so in 2011, we proposed and wrote a patent on this and said, here's a great thing. You can find the density from a measurement of the total collision rate and knowledge of the sigma V. There are some details, but that was the basic idea. And I guess we sort of felt like, okay, we understand now the physics behind this, and this proposal should make sense. And as inputs, you need to know sigma V, and you need to know this transferred energy distribution. Equivalently, you need to know sigma loss V. Okay, so in 2012, I went to NIST and I said, oh, you guys should do this because why not? And at the time, the question was, okay, well, that's great, but how do we know sigma V total? How do we know it? And how do we know that we know it? And at the time, it seemed clear there were two ways of getting at that. One was you do an orifice flow comparison, which is how you calibrate an ion gauge. The second was, well, you calculate it. Can't be that hard, right? So those are the two methods that were at play at the time. Okay, so as I said, so method one is as we calibrate an ion gauge, you can just put your atom sensor there, create some known density, measure the loss rate or the total collision rate, and just compute sigma total. That's straightforward. And then the second is, you know the interaction potential somehow, or you compute it, and then you solve the Schrodinger equation, the scattering calculation for the scattering amplitude, and then you plug that into your thermal average and you compute it, right? So those are the two methods. Okay, so in 2018, NIST sent us a calibrated ion gauge. And the plan was, well, let's just take that calibrated ion gauge, they sent it in the mail, and plug it into our cold atom sensor and just measure, measure the loss rate of the atoms and compare it to the pressure inferred by the ion gauge. So this is great, but they could only calibrate the ion gauge for nitrogen, and we wanted to run a bunch of other gases. We wanted to run hydrogen and helium and carbon monoxide and carbon dioxide. And anyway, so we wanted to run a bunch of other gases, but the ion gauge wasn't calibrated. So we're like, okay, this is great, but can't we do something more? Wouldn't it be great if the atoms told us the cross-section? That's a bold proposal, somewhat naive. And we said, you know what? They do tell us. And we wrote a paper on method 3, I'll call it, collision universality hypothesis. Okay, so this paper, that we had reason to believe that the atoms did tell us the cross-section. But let me tell you what the hypothesis is, and then justify some of why we thought it was this. So they're kind of, okay, there are 3 postulates in total I'll tell you about. So the first is that sigma total D, this quantity, is universal. By universal, I mean it doesn't care about the short-range physics. Now, this is an important assertion, because when you want to calculate the cross-section, you need to know the interaction potential. Knowing the interaction potential at long range is easy. You can solve that. You can figure that out using perturbation theory. At short range, where the atoms get really close together, their electron wave functions overlap, it's a many-body electron problem and many-body quantum mechanical problem. You can't solve that in general unless you have a quantum computer. No one has a quantum computer. So there are approximate methods for solving that problem. But the question was, how accurate are they? How accurate are they? And so this postulate, or this discovery, that the cross-section is universal, doesn't care about the short-range physics. What it means is that the quantum scattering calculations will give you the right answer, even if you've got the interaction potential wrong at short range. So the very part that's hard to calculate, if you got that wrong, you still get the right answer. Also, sigma loss phi is universal, meaning it also doesn't care about the short-range physics. So then the third postulate was, and this is the big one, the total cross-section can be obtained empirically from just measurements of this energy distribution. Remember I said before, the loss rate versus trap depth tells you the energy distribution, and the energy distribution should tell you something about what hit the atom. And our assertion was it should also tell you the cross-section. So why should that be the case? Okay, so I'll tell you in a second. First, why the insensitivity to short-range physics? So there's this beautiful book by Child, molecular collision theory, summarizing all of what was known, what was learned from atomic beam experiments, where they would cross atomic beams or molecular beams and look at the scattering products. And here's this picture showing the cross-section as a function of velocity. So in those experiments, you would have 2 cross beams. In the center mass frame, they were colliding at some relative velocity, and they would look at the cross-section. The total cross-section would vary as a function of velocity. This is velocity, that's the cross-section. It would wiggle. It would wiggle. It would oscillate. Those oscillations are related to the number of bound states in the potential, in the ground state potential. But let's just say it oscillates. And it oscillates because there's some interference between the scattering at long range and the scattering at short range. But importantly, this oscillation was around some kind of backbone, this dashed line, some trend, which is purely long-range determined. At some high velocity, you get a crossover where it follows a different trend, which is related to the short-range part of the potential. Okay. So yeah, so the oscillations are called Glory oscillations, but let's just say empirically that's what people saw, and they understood why that happens. And yeah, there's this transition velocity where it stops wiggling and following this trend and follows a different trend. And so the idea was, recall, we're measuring, or our atoms are sensitive to a velocity average. So it's the sigma, that's sigma, integrated, sigma times v, the collision velocity, integrated over the distribution of collision energies. This dv is the Maxwell-Boltzmann distribution. Okay, so it's an average. So this green swath here represents the range over which, approximately, where this integration has non-zero weight, where d has a non-zero weight. So you can see if I integrate over this wiggly thing, I average over a sine, I just get like 1/2. Well, if it's a sine squared, or if it's a sine, I get 0. So the contribution from the wiggly part goes to 0, and all you're left with is the contribution from this dashed line, which means, so here's an actual picture. This shows the full quantum scattering calculation results for the sigma as a function of velocity. This dashed line is the prediction for a pure C6 potential, so no short range physics at all. And this dotted line here represents my Maxwell-Boltzmann distribution. And again, when I average over this, I get a number that doesn't care about these wiggles. I get a number that only cares about what C6 is, which sets the slope of that blue dashed line, and the temperature, which sets the location of this peak here, right? When I crank up the temperature, this thing moves to the right and gets broader, but the averaging wipes away this oscillation. Okay, and then this is some actual calculations performed by Roman and company, where they took a molecular potential for rubidium and hydrogen, and they vary this molecular potential, its short range physics, by a lot. You can see here 3 different curves: the red dotted curve, blue curve, and the black curve. And the sigma as a function of energy, in this case, not velocity, looks like this. It wiggles as a function of energy. And the black curve corresponds to the black potential, the blue to the blue potential, and so on, the red to the red potential. And this band here sort of represents the range over which this average is being taken. When I average each of these curves, even though their oscillations are at slightly different phases and slightly different amplitudes, you can see the blue amplitude is lower than the black amplitude. The total cross-section is the same within 1%. 0.361, 0.361, 0.363. And this is after changing the potential by like huge amounts. Like, this is completely unphysical. You would never find a potential that looked like this. Anyway, so it didn't matter what the short range physics was doing. This average always gave us the answer you would get if you just considered the average over the pure C6 potential. Okay. Now, why should we be able to obtain the total cross-section empirically from measurements of the sensor atom momentum after collision? So this is just a straight up application of Heisenberg's uncertainty principle. So the idea is that the minimum momentum transfer will be related to the collisional size. So let me motivate this with a picture. So here's a picture of the de Broglie wavelength of my atom. This thing is large. It's like almost a micron in size because the atoms are moving really, really slowly. So they're like delocalized in some volume and space of over about a micron. The atom is like an angstrom or smaller, have an angstrom in size. But its position is not known because it's moving so slowly. Now, when it gets hit, this incident particle kind of finds the atom, sensor atom. It localizes it, and it localizes it to a zone whose size is given by square root sigma, this length scale. So you'd expect there to be an associated energy scale, which is just h bar squared over the mass of the trapped atom, the sensor atom, times sigma. Like the energy associated with, say, the harmonic oscillator is something like h bar squared over the mass times the sigma of the ground state wave function. That's equal to 1/2 h bar omega. And or said another way, if I put a particle in a box, if it's an infinite square box, the energy of the states, the ground state will have an energy which looks like something like 8 pi squared h bar squared over like the mass times L squared, where L is the length of the box. So this is just the confinement energy associated with putting a particle in a box of a certain size. When the collision happens, you localize the atom, it performs a measurement of its position, and now it's localized, and now it has therefore a larger momentum spread. And it can now get out of the trap because it's been kicked by virtue of this measurement. Now, you might argue that the collision also imparts momentum because, well, after all, the electron orbitals overlap and there's some force applied. but I'm saying even in the absence of that, even when the collision is at long range and a collision occurs, the minimum the collision will do is to localize the particle, and that kicks it in momentum. And the momentum wave function depends on the length scale. So the energy is something that tells you the cross section, sigma. So remember before we talked about, or I showed you the loss rate versus trap depth, and it follows this curve, which can be written as like the total rate times 1 minus P, or P is the retained fraction. It turns out that the median collision energy, this thing which is about 20 millikelvin, this median collision energy is, for a hard sphere, exactly UD. So a hard sphere has a classical cross-section which is pi a squared, where a is the radius. Quantum mechanically, averaged over all velocities, it has a total cross-section of 2 pi a squared. So half of the cross-section is classical, and half the cross-section is purely quantum mechanical. And in that case, the median collision energy is UD. Now, we don't have hard spheres. We have these atoms interacting with some van der Waals potential. So this is an approximate relationship. But we found that the shape of this curve actually encodes UD. So that was part of what this paper showed, was that this probability that the particle retained, this P function, is it's a function that only depends on UD. So anyway, so this is just, this is a bunch of details that are not important. We found we approximated this thing as a polynomial, and found the terms using some simulations, Lennard-Jones simulation, quantum scattering calculations with Lennard-Jones potentials, which turned out to be a mistake. But we'll get back to that in a moment. But the basic idea is you measure these points shown here in circles, the open circles, that's data, and you just fit them to this function that we just derived to find UD. And that's how you find the cross section. That's the way this works. So in practice, so here's some data. So here, this shows the loss, this shows the number of atoms, the logarithm of the number of atoms, some voltage, which is proportional to the number of atoms, as a function of time. So I can see an exponential decay, it's a straight line on a log line plot. When I add some xenon gas at pressure P1, I see this faster decay. And when I add a bit more pressure, I see this even faster decay. And so I measure the decay rate, which is just the slope, gamma. And then I repeat this measurement at those two pressures at different trap depths. And what I see is the loss rate decreases with trap depth because, of course, this P number, the retained fraction, is increasing. And for the higher pressure, I have a higher overall loss rate. If I divide these loss rates by the pressure, they fall on top of each other, as they should. And this loss rate divided by the pressure, I can repeat this measurement for different species. So here I show, so this is the loss rate divided by the loss rate at 0 trap depth, the total collision rate, which normalizes out the density. And here I have the data. So this data here for xenon is shown there in blue, and here's for argon, and there's for helium. And the argument was each of these curves is the same curve, just the x-axis is scaled by UD. So if I scale them by some UD, they all fall on the same curve, the same universal curve. The line there, that dark line is this polynomial fit. So I can find the UD just by figuring out what value, what scale factor makes them all line up. And this works for atoms. It also works for molecules. So here's hydrogen, nitrogen, CO2. These are data. All we did was scale the x-axis, and they all line up on the same curve. So we're like, oh yeah, great. This looks great. Does it work? So, okay, here's some numbers. Let's look at those numbers. So this is the collision rate coefficient, that's sigma v, for different species. Well, what do we have to compare it to? Well, we don't have a quantum computer. We don't have calculations. We don't have an orifice flow, but we did have an ion gauge. NIST gave us an ion gauge. What did the ion gauge say? It said that. So we were like, oh, great, this works. Surely this works. How could they, I mean, we did this blind. So how could they possibly agree at the 1% level or below if this didn't work? So we were confident that this was working. And it sort of works. Okay, so that was in 2018. In 2019 is the publication date. So 3 years later, 4 years later, the guys at NIST published some calculations. So they did some rigorous calculations, the interaction potential and quantum scattering calculations. And I say here, this work is excellent. And I kind of use a caveat here, which is, well, there are some uncertainties because, like, how do they know the interaction potential is correct? How do they know it? I don't know. And here are their numbers. So let's look at them. So in green is our QDU result. This blue circle is the NIST gauge that we had. And the red points are the NIST calculations. So the NIST calculations agreed quite well for helium. We didn't have a point for neon. And here our points were systematically below the NIST calculations. Okay. And then there was a big discrepancy for hydrogen. So what's going on? Right, yeah, so here, 25% disagreement. This looks pretty good. And these are all kind of systematically low. So we're scratching our head like, what's going on? Yeah, which is right? That's the question. Which one should you is right? So around this, a few months later, the guys at NIST also did an experiment where they have an orifice flow. They plugged in their atom sensors into the orifice flow, and they just measured, they calibrated the atoms, right? The same way they calibrate ion gauges, right? So they just did this experiment. How wonderful. So what do they get? Well, here are their numbers, but let's look at them. So here are the numbers in blue. These are the numbers that NIST measured using the orifice flow. So they got better agreement than our QDU result. Well, okay, let's go through the line by line. So, okay, so here they couldn't run hydrogen for technical reasons. So there's still this large disagreement. We now know what this is from. So before I told you this hypothesis required that velocity averaging, and remember this velocity above which things switch over and become short range dominant. Hydrogen is one of those cases where the gas at room temperature is moving so fast that it's beyond the crossover. So hydrogen is an example where the actual collision rate depends quite dramatically on the short range physics. So the QDU hypothesis shouldn't work. It also shouldn't work for helium. So this may be just coincidence. Neon we didn't run, but these other gases it should work. So yeah, so our prediction was systematically low. The NIST data appear to be systematically high. But so who's right? What is sigma B? How do we know that's the right sigma B? For what it's worth, this agreement here, I mean, this change here is like, it's like a 10% error. Ion gauges have like, when you ask like, how good is your ion gauge or your residual gas analyzer, it's not good to a factor of 2. So 10% was like wildly successful. So even though this is different and disagreement, this agreement is like fantastically good compared to every other method for measuring pressure at UHV. Still, you'd like to know what the right answer is. Which number do you pick? Okay, so we went back and looked at our hypothesis and said, something's wrong here. What's wrong? Are these correct? Are these postulates correct? Is it universal? And also, what's going on? So we looked at this again, and indeed it is universal, but only for heavy or slow collision partners, which is why hydrogen didn't work. It's moving too fast. And but we found that the collision cross-section can only be estimated looking at the transferred energy distribution. And for a reason which is a little bit subtle, but it turns out that the collisional transfer energy distribution only gives us information about C6. So the Heisenberg uncertainty principle argument that I gave you before, I said, oh, the momentum distribution at low energy is fixed by the total cross-section. And the total cross-section, we presume is, yeah, the average. But it turns out, no, actually, it's the C6 cross-section that matters. So it's almost like, well, okay, it's almost like when you look at the momentum distribution at very low energies, you're only really probing the collisions that are at very long range. And those long range collisions only really see the C6 part of the potential, this long range C6 part. They don't probe the short range physics. So, okay. Now, and in addition, there are other terms. There's like a C8 and C10, which are also kind of long range, which also affect the cross section. So even though the cross section is universal, meaning it doesn't care about what's happening at really short range, it cares about kind of the long and median ranges. And because we only get information about the C6, and there's also additional contributions from C8 and C10, we will systematically underestimate the cross section using the universality method. So we figured this out. We figured out what we did wrong previously. We used a Leonard-Jones potential. We should have used something a bit that had other terms. We would have seen this immediately. But live and learn. Anyway, so here's a picture, by the way. So here's our data in red dots. And here's the measurements that we made. Sorry, yeah, the data's in red dots. These circles are the C6 cross-section that you would compute just using the kind of the known values or the believed values. And so you can see our data kind of follows these little yellow circles quite dramatically, right? Even for hydrogen, where it completely disagrees with the full quantum scattering calculation. It turns out that the cross-section is lower when you include short-range physics because of some interference effects. It's kind of weird. That's quantum mechanics. So anyway, there's a lot of details here, but I'll just say that the punchline was the collision transfer energy only provides information about the ultra long range part of the potential. Okay. But we still have this question, which of these values should we believe? So we know these values here are underestimates, but we have these values. Which should we believe? How do we know? And how do we know, like, how would we possibly answer this question? You might say, well, you redo the calculations or you redo the measurements. We chose something different because we can't do the measurements when all of an orifice flow. And my theory is not as good as the guys at NIST. We did this. Okay, so what did we do? I'll tell you. So we noticed that at NIST, when they ran their measurements, they had two sensors, a rubidium sensor and a lithium sensor, and then the orifice flow, and then they had a pipe connecting them. When I thought, oh, you know what, that pipe, that's that could introduce like systematics, because like, what if the pressure here was not the same as the pressure there, right? Because there's some flow of gas, maybe the temperature here is different. Indeed, the temperature was different, right? So we worried about differential vacuum effects, maybe the temperature different, maybe the analysis didn't account for the ensemble energy distribution evolution. So there are a lot of like questions. So we said, well, what can we do? We can do this. We can put the atoms on top of each other in the same trap, okay, not simultaneously. So they're probing exactly the same gas. We don't need to know what the pressure is because all we care about is the ratio of the cross sections. I'll tell you that in a moment. So, but crucially, there's no difference in the vacuum. There's no difference in the temperature, but we only get the ratio, the cross-section ratios. So we did this measurement. So here, this shows like the loss rate as a function of time. We like turn on some gas. This is the loss rate of rubidium in red and the loss rate of lithium in blue. We this is hydrogen. We had a high pressure of hydrogen, then we turned it down, the loss rates went down. So this line here is the residual gas analyzer measured pressure. We turned down even more, then we turned it up, then we turned it up, then we turned it up. So we kind of randomly vary the pressure and measure the loss rates. And the ratio of the loss rate, so if I plot the loss rate of rubidium and the loss rate of lithium, the ratio of the loss rates will be the slope of that line. And we did that for hydrogen, and we did it for helium, did it for a bunch of gases. And we saw curves like this, right? So this is the loss rate of rubidium and the loss rate of lithium. And here's all the points. And you can see the ratios are different. And if I plot the ratios, okay, here are the numbers. Here are our numbers. If I plot the ratios, okay, this is what we get. So for hydrogen, in green, I show our ratio. This is lithium-6 hit by lithium-6 and rubidium-87 sensor atoms hit by hydrogen. The green points are our measurements. The blue points is the NIST theory. Now, they were doing calculations for lithium-7. They're an isotope. The potentials are basically identical. The cross-section should not at all be different. And we can see there's pretty good agreement here. Don't worry about these other 2 points. The NIST experiment couldn't run hydrogen, remember I told you, so they don't have a point here. But we can see there's pretty good agreement. Here's the theory and the error bar for the theory, and here's our measurement. The error bars are smaller than the dot size. Here's what we saw for helium. So here the theory is below both experiments. This is the NIST experiment and our experiment. The NIST experiment is in orange. Ours is in green. Neon, we got this number, which matches the theory, which also has giant error bars, so it matches the other experiment. You might wonder who's right. That's the question. Here's our measurement for nitrogen, the theory and the experiment. Again, these are ratios. Argon, our measurement, theory, measurement, NIST measurement. Krypton, our measurement, theory, NIST measurement, and xenon. Now notice something very conspicuous. So here I show, this is an inset of showing these points here. Our measurements in green are almost all identically the same. The ratio of, so when nitrogen hits lithium-6, or when it hits rubidium, the cross-section ratio is 0.796. So lithium is ever so slightly smaller than rubidium from a cross-section standpoint. And they're all the same. And the calculations are also all the same, but systematically lower. You know, the experiment is kind of bebopping around. That's probably, those fluctuations are probably because they had differential vacuum problems, and maybe we don't have those problems. Our measurement error bars are like super tiny. Like we could get extremely precise measurements because we didn't have any of these other effects. Why is this? Who's right? What's the right answer? Okay, so Roman and Shuyang and Jim and I looked at this question and did some other things. And one of the things that we found was that if you just change the C6 coefficients of lithium and nitrogen and rubidium and nitrogen by like 5%, you can bring these into agreement. So maybe they just had the wrong C6 values. Maybe the potentials are wrong. I mean, maybe our experiment is wrong. The fact that we get like fantastic agreement with their hydrogen result makes me feel like our measurement is good, because I believe their hydrogen result. Hydrogen, by the way, those approximate methods, remember I said you need a quantum computer to la la la. For hydrogen, you can almost do this calculation rigorously, even if you don't have a quantum computer, because it doesn't have many, it's not a many electron system, like hydrogen hitting lithium. Hydrogen hitting rubidium is an many electron system. But anyway, but you might argue that this blue point here is a good point. And it matches with an error bar our measurement. So this discrepancy here is a question. What is it from? Yeah, so this is some of the work that I described where we were looking at if you just say change the C6 values. But it's still a mystery. And for metrology, you want to, I mean, the name of the game is to do things better, measure more precisely, and really understand your error bars and understand from first principles what should the cross-section be. But I hope I've convinced you that we now have a primary standard. By primary, I mean this standard does not need a manometer, mercury manometer. You can, from first principles, calculate sigma v and know the density. So now it is possible to measure, in principle, any gas in a vacuum or any flux of any particles in a molecular beam epitaxy experiment and know it in an absolute sense, without calibration drift, without error, with some uncertainty based on, these numbers I've told you, which is on the order of 10% or less. So I've talked for a long time. I want to talk more, but it's now too late. The one thing I would tell you about is our latest work using position entangled states. We wanted to basically have our background gas hitting things more exotic than an atom. And we use position entangled states for that, which I can explain later, but I think I don't want to overstay my welcome. So with that, I'll thank you for your attention. And if there are any questions, don't hesitate to ask.
Yeah, so are there any questions for Kirk?
I'm here in SFU about question. Karen.
Can you hear me?
Yes.
Yes. Yeah. Great.
I'm an experimentalist, and now we're looking at your talk as a great example of the new pressure sensor. How easy is it for me to put it on my ultra high vacuum system, whatever it is? I have a couple in electron microscopes, for example.
Great question. So at present, it's hard because there's no one builds a turnkey cold atom system yet, and they're not so miniature. It's like an optics table full of lasers and whatnot. But NIST has been doing a lot of work miniaturizing these systems. They've built a device, at least they've built the vacuum part of the device to be the same size as an ion gauge. But there's a box of electronics and lasers that sits next to it, which is like, a meter by a meter by a meter. And until that's shrunk down to, a rack mounted control system, it's probably not so feasible. So anyway, there's no commercial entities that are building these things.
But okay, you have one over in your lab there at UBC, right?
We do, yes.
So-
It
Have you hooked it up to some MBE machine or something else that you're using for some real experiments?
Yeah, we haven't yet. So some time ago, Kutsu and I were putting together a CFI application, which unfortunately didn't get funded, to do exactly that, to apply this sensor to MBE. And we had reason to believe that it would be useful. And I think what Ko was saying was, for him, I think there's certain sources which are really hard to stabilize. For example, if you're growing ruthenium or you're using tungsten, you have to use I guess it's electron sputtering to generate a beam of those materials. You can't just have a crucible that you heat up. And so he was saying that controlling the flux of those in an absolute way would be quite helpful. I've heard anecdotally from years ago, Tom Tiji told me that there are certain processes where you're growing a certain material, and the stoichiometry that you need the flux of your sources that you need to tune to get the right stoichiometry changes depending on the growth rate. So he said. So there was some potential benefit to being able to measure in an absolute sense the fluxes in situations like this where, but we haven't tried this yet, in large part because of we need the money to do it.
Well, yeah, I guess you want to know the pressure at a particular location in your chamber as well. I don't know how easy that is.
Yes. So,
Varies depending upon where you are as well.
correct, yes. And these atom clouds, you can move them around, right? Like you can position them, and they're quite small, right? Like, I mean, when they're in the magnetic trap, they're a few millimeters in size. And so you're really measuring either a local pressure or a local flux. And these can be moved. So it's not a large volume sensor like a ion gauge. It's it has effectively a very small volume, which I guess is, good if you're interested in, say, for example, measuring the uniformity of your molecular beams across your sample. You could do that. You could, in fact, we did a measurement where we had a molecular beam, but it was of hydrogen, and we were measuring. So this was like a supersonic jet where we were generating a beam of hydrogen gas and measuring the profile of the beam using the atoms. So that's the closest thing we've come to like an MBE application.
Thanks. You can put one on my machine anytime you'd like.
Okay. Thank you for the offer. Yes, I think we have a portable, cold atom sensor that we brought to the PTV in Germany. And the goal was to repeat the kind of measurements NIST made, but using a different orifice flow system. In Germany, they can flow hydrogen, for example. And so we brought it there, and then we blew it up, so we had to fix it. It's presently now at UBC. So it is conceivable that we could wheel this thing over to your lab and or in a car, I guess, and hook it up. But we need to fix it first.
Did you say it blew up?
Yes,
Hydrogen explosion, you mean?
no. So we use water-cooled electromagnets to generate the magnetic field that we hold the atoms in. We hold them in a magnetic quadrupole trap. And the postdoc who was helping me, we got the whole thing working after some months of it being down. We don't live in Germany, so we had to go there. And then when I left, he accidentally left well, there was some malfunction in the interlock. So the electric current was still running in the coils, although the water cooling had turned off. And so the coils overheated, and I guess it didn't blow up, but it
Melted.
Figuratively, yes. Yes. It melted a bunch of plastic, and yeah, it was a mess. So
Those postdocs can't rely on this.
I feel bad for him because he did the same thing on his apparatus as a PhD student. Yeah, but the second failure was not his fault. I mean, the interlock, something about the interlock. Anyway,
Okay,
water under the bridge, but yes, yeah. So we're now fixing it. Was that a question?
No, I'm just wondering whether I'm the only one asking questions or wants to ask a question.
Are there questions? Oh, there's a question in this room. Yes.
You mentioned it, but what is your next goal in the field?
Yes. Okay. So the question is, what's the next goal? Yes. Yes. Okay. So I'm going to zip through this to get to the end. The next goal. Okay. So there's, so I've argued that orifice flow comparisons, quantum scattering calculations, and the quantum universality are three different methods for knowing sigma v. Cross-section species comparisons is a way of knowing what we know, knowing that we know. The next directions are to extend the sensor to higher pressures and to, say, study the decoherence in atom and ion-based qubits. So, so extending to higher pressures may involve using, so the challenge of going to high pressures is that you need your quantum state preparation and your readout to be fast compared to the collisions, right? You need to prepare the system, know that it's in some state, hasn't been perturbed, measured at some later time after it's been perturbed. If you get collisions during the preparation, it complicates matters. And so when you go to higher pressures, the collision rate is much, much higher. And the typical preparation time for laser cooling, the time it takes to actually get the atoms to coalesce at the center, is on the order of tens of milliseconds. So we can't measure pressures above like 10 to the minus 5 Pascal. So the idea here is to use just a room temperature vapor, and we don't prepare the atoms by putting them in some motional state, but rather we take the atoms and put them into some other states, an internal state, and look for collisional decoherence, if it's a superposition, or state changes. So for example, we might use a Rydberg. We might take the atom and excite the electron to some highly excited orbital. There, the cross-section is much, much larger, and the state preparation can be very fast. It's an electronic transition. And then, yeah, you would look for state changes after the preparation. And yeah, so that's one of the next steps. And Rydberg atoms are kind of an exciting topic right now, and this is like a new application. And that this decoherence study is, I think, very interesting. You know, as I mentioned before, ion-based quantum computers, ion-based qubits, are subject to background collisions. The ions are held typically in very, very deep traps, so they don't get lost. They're hit, but they don't leave the trap always. The loss rate is very low. But nevertheless, you might wonder what happens to the information you've stored in that qubit. You've stored it in the nuclear degree of freedom. Could there be decoherence because the collision somehow like gives you which path information or gives you which state information? And then also there are protocols where in an ion qubit you require there's some during the operations in a 2-qubit operation in many ion-based quantum computers or quantum qubits, the 2-qubit operation involves some motional state and some internal state of the ions. And so if you had a collision during that event, of course, that could also mess up your 2-qubit gate. So the question is, I guess, like, you know, how do these collisions perturb those systems? And I think it's still not well known, but that would be a next step for this field. Any other questions? If not, I'd like to thank you all for attending and thank you for your attention. And if you have any questions and want to talk to me later, don't hesitate to write me an email. And maybe I'll schedule another talk where I can talk about tangled states. But thanks so much.